Okay. So you may have heard about this. So CCP4 Cloud is a new way of using CCP4 that we're just about to release through CCP4 7.1. And what I'll do is I'll give a very brief talk about what it is, and then I'll try and show you how to get started with it by doing a demonstration. So the CCP4 Cloud was a BBSRC grant project that we did a few years ago, and it's mostly been developed by these two chaps, by Eugene and Andre in our core team. And the idea was basically to produce a cloud-based way of doing structure solutions. So what's that mean? I mean, we do many things online nowadays, such as banking and buying things through Amazon, or paying our bills, or storing documents. So why not do the same with structure solution? And it's due to be released in CCP4 7.1, but you can try it now if you want, and it just requires a little bit of additional software installation, and I'll show you where to get that. The main advantages of it are that you can get access to big computing resources, and also use the software online rather than having to have it locally installed. It has you might have used CCP4 Online, which is very much about big programs that take a long time to run, such as Morda or Mr. Bump or Ample. Well, CCP4 Cloud takes things to the next level, where it includes project management for your structure solution. So it has a nice way of viewing what you've done, which I'll demonstrate. It also includes storing all your data. You don't have to worry about file upload and that. Everything, once you upload initially, everything is done online. It's accessible 24 hours a day, 7 days a week, and from anywhere that you have a Wi-Fi, you should be able to access the cloud. And it can also integrate well with other steps in the crystallographic pipeline, such as data collection at the synchrotron, where you can pick up your images directly from the various databases that the data stores that the synchrotrons might have, right through to deposition. It includes a deposition task where you can set up things to deposit directly in the PDB. So it's all done through a web browser, and it has a project interface like this where you list your projects. Each project then has a tree-like structure where you can see the jobs that you've run. You can run down through each of the steps that you've taken in structure solution. And then each job itself has a nicely formatted report page where you can view graphs, and you can look at numbers, and you can launch browser-based viewers to see how things are going. And you can even run it on your phone. It wasn't designed to be used on a phone, but it does work, so you can at least log in and you can look at results, and you can even launch jobs through a smartphone. So the main aim of where it's going to be used is on the cloud. So there are 3 ways you can actually use it, but it's not meant as a direct replacement for CCP4i2. It's mainly aimed at installations in big institutions, so places like the Crick and synchrotrons like Hamburg have installed it and used it as a resource for their users. And also we have a centralized server in Oxford at the lab where you can submit your jobs to our clusters. But it can also be used locally. You can run everything locally on a single machine if you need to. I just make one other point before I go on to the demo. So there's a few things that you need to get your head around before you use it. And there is no file system in the cloud. So what you have is what's called a revision. And a revision is essentially everything we know about our crystal structure at any point in the process. So for instance, if you're at the point of scaling and merging your data, you know your set of reflections and you know your cell geometry. But you may not know your phases, and you may not know you won't have coordinates, but you could have sequence, for example. So a revision at that point will contain the reflection information, the cell geometry, and the sequence information. But then we need to add to that revision a coordinate, or to a later revision, we will add the coordinates through model building. So just bear that in mind. Okay, so I'll attempt to do a live demo, which is a bit risky in a room full of people using the internet, but we'll see how we get on. So what I'll try and do is I'll try and solve this structure, which is MDM2 from Martin Noble's group. It's a nice small structure, so hopefully we can get through it pretty quickly. It's a small protein bound to a ligand, and we have the reflection data available so we can show how to process the images. So if you want to install it yourselves, if you look for CCP4 Cloud on the internet, and it should be there somewhere. All right, here it is. You'll see this login page. So you can log straight in here, register and log straight in, and you can use various applications online, but it doesn't include everything. So if you really want to use it comprehensively for structure solution, I suggest you install the CCP4 Cloud client, which is available for Windows, Linux, and Mac. As I said, this will be in CCP4 7.1, so you only need to do this if you want to try it today, but in a month's time or so, it will be in the suite. And once you install that, you end up with these three icons on your desktop. One is just for configuration, and then these two are the two different ways you can run it. So you can run it locally using this desktop icon, and the plane here is meant to symbolize airplane mode, like as if you were in an airplane. But this one, with the Wi-Fi symbol, means use the cloud properly. And the advantage of doing it this way is that there are some applications like data processing and things like Qt and CCP4MG that will enhance the experience by being able to run them locally. So if you double click on the cloud icon, it takes you to the login page, but this time it's integrated with your local CCP4. You can register quite easily and quickly. So I created an account yesterday. And we can log in. And the first thing you'll see is this projects page. It's all designed to be fairly simplistic, so it's easy enough and intuitive to get started with. And to create a project, then what I will do is I go add, and I'll call it MDM SW project ID, and I'll just give it the same project name. And that creates a new project for me. Before I move from here, there are demo projects that you can have a look at if you want to see how it works. So it's sort of tutorials. And there's also a help button which gives you information about how things work. So if I double click on my project, it takes me into the project area. And now I'm presented with a list of possibilities of what I can do. So by default, it gives you a set of suggestions. So here it's given me applications like ZIA2 and dials, or importing from the PDB as a guess to what I'm actually going to need. But there's also a full list of things here listed. It doesn't include yet everything that you can do in CCP4 I2. It's meant to be more coarse-grained than what you can do in I2. But there are some things like Archamboldo and ARP-WARP that aren't yet in here that we'd like to have. So the first thing I'm going to do in this project is I'm going to run ZIA2 to process my images. So by clicking that, I get this interface, and then I just need to give it my image directory, which I have all my images here. So I just point it at the image folder and just click run. Most things are defaults are set for you, so you don't have to really adjust much. And that goes off, and it's now running dials underneath and pointless and aimless to do the scaling and merging. And now that is running locally on my own machine because images are so big. It's not efficient to be uploading all our images to the cloud and then processing them. But if you use Diamond, for example, it is integrated with the iCat database at Diamond for accessing images. So in big institutions, if you have a centralized image store, you can integrate it with that, and you can do all of the image processing on the cloud. You can also, if you wanted to, run local applications like dials. So I can run Dewey, and it gives me that, and I just press run, and I should get a Dewey interface. And again, I could do something like pick out the images for this case and import them into Dewey. So as David said, Luiso will give a comprehensive overview of Dewey in his lunchtime bites, so I won't do any more with this, but just to show you that you can do it. And when you go through and you create an integrated MTZ or even a scaled MTZ file, it will import it automatically into the cloud for you. So while ZIA2 is running, I think it might take a little bit too long to process, so I do have a resulting MTZ prepared. And you can come into the cloud at any point, so you don't have to start at the images. You can have a merged MTZ that you may have taken from a Diamond visit or anywhere else. And you can import your files. So what I'll do is I'll add a new job and I'll import the files I need to solve this structure. So I press data import and I hit upload local files, and I have all the files I need here. So the things I need are the sequence, what else do I need? This has a ligand, so I'm going to take the ligand as a smile string from this HTML page. I can also read PDF documents, and I'm also going to take a merged MTZ file that will ultimately be produced by my ZIA2 task. I could take the unmerged and run scaling locally, but I think given the shortness of time, I'll skip that step. But if you wanted, you can take an unmerged MTZ and run the aimless pointless task to scale and merge it. So when I run this, it spots that I have a sequence, and it asks me whether it's protein or DNA or RNA. So if I had a mixture, I could set whatever type of macromolecule they are. I press apply and upload, and now it's uploading those files. And you need to run this import to actually import it into your project. And then you get a report. And based on the file type, it knows what to do with it. So in this case, I've given it an MTZ and a sequence. And I can see details about my MTZ file. Note that in this case, it goes into P6122. So there's an enantiomer for P6122, which is P6522. And at this point, we don't know which one it is. We can only find that out in the phasing step. So when I do molecular replacement, we'll try both space groups. It also gives you various plots, such as the C-truncate plot, and you can look at things like whether it's twinned or whatever. So standard sort of output from scaling and merging and generating amplitudes. So you also have the option to run things like view HKL to see the headers from the MTZ, or you can actually, if you wanted to, you can download the files that it's produced by expanding on this tab, and that is available in every task. So at any point you can access the files it's producing. It also gives me the sequence information. And because I uploaded a few other different files, such as the PDF file, it will present those to me in a relevant viewer. So this is the PDF for this particular tutorial. And there's also the HTML version, which includes the SMILE string that we'll need for fitting the ligand. Okay, so Dia2 is actually finished, so I could have worked from there, but I'll start from this point. So the first thing I need to do is create a revision that includes details of the reflection file and the sequence. So that is basically creating what is the asymmetric unit contents. So I add a new job, and I'm given this in the suggested list, which is the asymmetric unit. And by automatically, it's loaded my reflection file and the sequence information. And all I need to do is press run, and it will try and figure out how many copies of that structure there are, given the cell dimensions. And in this case, it's a single copy with a solvent content of 64%. So that's created for me the first version of my revision, the first revision for me. So now what we need to do is we're going to do molecular replacement to find the phases and also create the initial coordinate file for our target. So to do this, I can add a new job, and now it's figured out that maybe I want to do molecular replacement, and it's given me the option to run programs like Morda or Balbez or Mr. Bump, which will do automatic molecular replacement. But what I want to do is I want to do it more manually. So what I'll do is I'll run this task, which you may have seen in the I2 interface, which is the CCP4 MG molecular replacement model preparation task. And it gives me a small interface where I can change a few things, but I'll just run it on as it is. And that fires up locally on my machine, the CCP4 MG interface. And it's running Mr. Bump underneath to find potential search models. And then it's giving me a list of hits. The coloring here is based on the score from the alignment program, but future versions of it will show the sequence identity. And in the 3D viewer, I see a alignment between the best models. And we can see that it's actually picked up 4HG7, which is reassuring that it's found the right one. And the nice thing about this tool is that if you have, you can create single models from it. By whatever you see in the viewer, you can save as a model. So you can adjust what you see. And Stuart will give an lunchtime bite about how MG and all the features that it has. It's very comprehensive. But in our case, what I want to do is just create an ensemble model for use in Phaser from this alignment. Should note as well that these models have already been through the Sculptor program, which truncates the side chains based on the alignment and cuts away those loops that may differ. But here I have this nice tool that if I slide this slider, it trims away the most variable bits of the aligned structures and gives us a nice low variance core region, which is probably the most similar part of these models to our target. So what I'll do is I'll save that as a search model for molecular replacement by just clicking on Save All Visible to CCP4 Cloud. And then I can exit this task. And it's, because I ran it locally, it uploads the model to the cloud, and it's now saved. And I can use an application like this Ugly Mall browser to just see what I've actually saved, and that looks good. Okay, so I now have a model and I have reflection data and I want to do molecular replacements. So I add a new job. In this case, took a guess and said I might run phaser, which is what I'll run. And it loads up the phaser interface, and most things are set automatically. As I said, this target, this space group has an enantiomorph. So what I'll do, I could ask phaser just to try all possibilities, but just to show you how you can run multiple jobs in the cloud. And one of the great things about using the cloud is with the big compute resource, you can just fire off lots of jobs. So if you're dealing with a difficult case, there's no worry about overloading your local machine. So what I'll do is I'll run it in both space groups. I'll run it in P6122, and I'll show you how to re-index into 6522, and we'll run it there as well. We know there's one copy, and the homolog has 100% sequence identity because we actually found the true structure, but in this case, it's for demonstration. So I run that, and that's launched the job on the cloud. And then I'll come back and I will add another job to change the space group. And it's figured out that probably that's what I want to do. So I press, if you want to define that, you can go to our list, and under asymmetric unit, there's change space group. And it automatically sets to the enantiomorph P6522. I run that. And that will create a new revision with the data in 6522. And then I can add another phaser job and tell it this time run in 6522 and run that. So that just shows you how you can just launch as many jobs as you want, and there's no overhead. So while they're running, I'll create the ligand that we need to fit to the map. So if I go back to say so you can see that it's building up a tree, and you can add jobs at any point in that tree. So what I'll do is I'll add a job to say the asymmetric unit task, and this creates a new branch. And what I want to do is create the ligand. So I'm going to run astrug to generate the restraints, and that by default asks me for a smile string. So back in my import stage, I did have the smile string. So if I copy that, I can paste it in here and just run that. And that will go off and run astrug to generate the restraints and things we need for fitting the ligand to our map. So in the meantime, phaser's running in the two space groups, and we can have a look at the reports for those two jobs and compare them and see if we can spot which one is actually the correct space group. The first one is, it's at the refinement stage, and it's not looking too good. I mean, the log likelihood gain scores are pretty low, so chances are that's not correct. Either our model is not good or the space group is wrong. If we have a look at the other one, this is also at the refinement stage. And here it looks a lot better. So we have a log likelihood score of around 150 so far, and our factors are dropping below 50. So it looks like P6522 is the correct space group, and we can compare those two reports side by side. So hopefully they won't take too long to finish. Our ligand has done, so we can double click on the ligand job and we can take a look at what it's created. So there are the options to run CCP4 or uglymol here, or we can even download the coordinate file, but we'll just use the uglymol application to see, and that's what has been created for us. So that looks good. All right. So we're just waiting on the phaser jobs to finish. What else can I show? It includes most things you can do. So there is also a deposition task in here somewhere. If you get to the end of refinement, like Hugh showed with I2, that you can run the validation task and it prepares everything you need for deposition. And it even gives you the report from the PDB as well. So we've had one phaser job is finished, and that looks pretty good. That's P6522, and our log likelihood scores are very good. And in P6122, they don't look so great. So we'll continue with P6522. Let's do a little bit of refinement. With RefMac, we run 10 cycles. And we can have a look at what phaser has produced. So again, we just take a quick look with UglyMol. It loads up our model, and it also loads up our map. And I can expand the map, and we can see that that looks pretty good. We've got obvious solvent channels, and we've got difference map density where the model doesn't show everything that's in the target. And probably in there somewhere we have a density for a ligand. It's not quite clear yet, so refinement should tidy that up a bit, but that looks to me like the ligand density there. I think that's the ligand there, but we'll see after refinement. With this kind of resolution, you can also use other things. So density modification is always very useful after molecular replacement if you've got this resolution, or you've got things like non-crystallographic symmetry. So I could run a program like Acorn, which will improve the map for me, essentially. So I'll run that. But as we can see from RefMac, the refinement scores look pretty good. So let's have a look at the map. And yeah, it's looking a lot better now. And there's bits of main chain that haven't been built. And somewhere in there is a ligand as well, I guess. Yeah, there. So that looks like our ligand. So what I'll do is I'll run Coot to try and fit that ligand. So we can add a job to the RefMac job. Hang on a second, I didn't do one thing. So as I created the ligand in a different branch, what we need to do is actually select both the refined result and the ligand output in order to bring the ligand into our Coot job. So I select both of those and I add a job with Coot. And here it's loaded the output from RefMac, and I need to tell it use this ligand. And we run that. And that will. So one thing to note about using Coot is that when you use it through the cloud, always save the output PDB file. It doesn't automatically pick it up. You need to save it out. Just save it anywhere, but save it. And that's what that message is about. So here's our ligand. Here's our density. And the quickest way to get it in there is to use the other modeling tools, find our ligands, and then make it flexible and select our ligand model. And let's place it right here. And we run that. And it shouldn't take too long. What it's doing, there we go. That looks good, so okay. And there we are, our ligand is fit, and it's gotten a bit wrong up there, so I'll try and fix that. All right, it's a bit better. And then we can just merge that in, merge the model in. I'll get rid of the copies that we don't need. And then we save that model. So save coordinates, select the file, and just save. And when we finish Qt, that should load that model back onto the cloud. And I can just verify that by looking an ugly model again at the output, and there a ligand has been added, and it's ready for further manual model building or refinement, and ultimately for deposition. I think we're just at this time now. So that's basically a brief introduction to how to use cloud. Eugene and Andre are going to be at the lunchtime bite session. So if you want to give it a go, or you want to hear more about it, please come along to their bite sessions during the lunch times. Okay, thank you. Probably time for one quick question if anyone has a question. Sorry, Craig.
Could you comment on security on the cloud if it was a confidential ligand you didn't want anyone else to look at?
Yeah, depends where you use it. If you use our cloud, then, I mean, it does now use SSL security for the access, but we're conscious of the fact that many commercial users won't want to upload their important ligands and data to the cloud. So you can either run it on a local cloud or use it locally on your own laptop. So that functionality is there. Sorry, I can't. How long is it stored on the cloud? So we implement a policy where we provide users with a quota, because we can't provide infinite amount of resources. And if you haven't used the project within so many, I think it's 6 weeks, or maybe it might even be 6 months, then we remove the data. So it persists for about a few months. But if you've not been using it, then we will delete it. Okay, I think we're over time, so probably we should move on.